so that we can get started. You are witnessing something extremely rare at AGU, and that is two Raymonds on the same platform. I doubt that's happened very often. My name is Raymond Bradley. I'm from the University of Massachusetts, and I'm vice chairman for another 25 days and counting, vice chairman of the Global Environmental Change section. And it's my pleasure to introduce this year's Tyndall lecturer, Ray Pierre Humbert. The Tyndall History of Global Environmental Change is our second named lectureship for the GEC section. John Tyndall was a consummate physicist. He was an Irish physicist in the 19th century who, among other things, began his career studying magnetism. He also studied radiative processes. He published monographs on heat and sound and light. He also, interestingly, was a glaciologist of sorts, and he published an interesting series of books, including one on called Hours of Exercise in the Alps, which was a very good seller, and it still is, as a matter of fact. We honor John Tyndall for his work on understanding or examining in an experimental way the important role of carbon dioxide in radiative processes. And we have established this lecture series to honor scientists who have made contributions to global environmental change studies in general. And it's my pleasure today to introduce Ray Pierre Humbert, who is the Lewis Block Professor in the Department of Geophysical Sciences at the University of Chicago. He received his undergraduate degree from Harvard and his PhD from MIT. His expertise is in the physics of climate, and not just of the Earth, but of other planets. He has, among his many honors, he's received a Guggenheim Fellowship. He's a fellow of the AGU. He's a Chevalier de l'Ordre des Palmes académiques, and he has I think the right term is a boatload of publications, pages and pages of very important, very significant papers, in many of which, of course, are in AGU journals. And he studied everything from snowball Earth to the climate of other planets. Today he will discuss successful predictions, looking at the role that people have, the way in which people have tried to anticipate how the Earth system will change in time and how successful they have been. And it's my pleasure to present Ray with the Tyndall certificate and to introduce him to you. Thank you.
How do I switch this over? How do I switch this over to my? So.
Now you're asking.
Yes.
Let's see. We have to. How do we switch it over? Good question. That I never found out. Just do this. How's that?
No, not that.
Where's you got to switch it? PC to Mac.
Where's that down here?
Oh yeah. Okay, that's fine. Okay, good. Thank you very much. A few years ago at the American Geophysical Union, Naomi Oreskes made a remark in a talk that you climate scientists are so busy talking about stuff you don't understand that you never get around to taking credit for the things you got right. And I got kind of prickly. I hemmed and hawed. I said, well, of course we do. Well, maybe she's right. So when I had to, I hate being wrong. But we recover from it. And so when I had the opportunity to present this lecture, I thought I would build it around instances of successful predictions in climate science. Now, Climate, what do I mean by a prediction here? Climate science is not an experimental science. You can't actually do a controlled experiment on the collective behavior of the whole system any more than astrophysicists can do a controlled experiment on stars. Now, of course, we're doing a kind of uncontrolled experiment on our own Earth by changing the composition of the atmosphere, but we only have the one experimental apparatus, and unfortunately we have to live in the beaker while we're doing this, which is not such a great thing. We have to wait a long time to see the results. But nonetheless, we do refer to predictions that we make. Sometimes when we say predictions, we mean things that are just consequences of our theories that we can check against observations. But the most convincing predictions are those consequences that are predicted before the observations are actually available, and that's what I'm going to concentrate on for the most part. So the granddaddy of all predictions in our subject is the prediction by Arrhenius that fossil fuel burning will cause an increase in the atmospheric carbon dioxide, and that will cause a significant warming of the planet. And this is a cartoon version of the one-layer climate model that Arrhenius used to turn this conjecture into a set of numbers. And I'm not going to go through the details of it, except to point out how remarkably many things Arrhenius got right in this model. Now, as we know, the Earth really is warming, and it really is due to CO2. I'll come back at the very end of the talk to that particular verification and the extent to which we can fairly say that was predicted quantitatively. So, among other things, Arrhenius, what I want to highlight is that Arrhenius realized that the temperature is determined by a energy balance of solar energy in versus infrared out, and that you need to determine this balance by satisfying the top of the atmosphere radiation budget. And this is something that Fourier already knew in 1827. He knew that the infrared opacity was due to CO2 and water vapor, that water vapor is a feedback, whereas CO2 is a forcing. He knew about the logarithmic relationship between CO2 concentration and temperature, and that the greenhouse effect works by the atmosphere radiating to space at a colder temperature than the ground. All these things are sufficient to correctly get the sign of the effect, but there are some things he didn't get right. Well, he got the whole conceptual framework right because of the limitations in the knowledge of spectroscopy of water vapor and CO2 at the time. He could not get the quantitatively right prediction. And what's more, the one-layer atmospheric model he was using was not sufficient really to quantitatively address the competition between water vapor and carbon dioxide, which we'll come to next when we talk about Mr. Knut Ångström. This is the son of the Ångström unit, Ångström, and he made a false prediction. So it's important to talk about what predictions were wrong and which predictions were right. But based on laboratory experiments, Knut Ångström predicted that carbon dioxide would not have a significant effect on climate. And he predicted this on the basis that the infrared absorption due to carbon dioxide was saturated, that Earth's atmosphere was already absorbing as much infrared due to carbon dioxide as it could. And he also predicted that any effect that carbon dioxide had would be completely masked by water vapor. And he was wrong on two accounts. One was that his laboratory experiments were simply not accurate enough to see the incremental absorption due to CO2. The Earth's atmosphere is not actually saturated in the sense that he thought. Even the Venus atmosphere is just barely saturated in the sense that Ångström thought. But even if his experiments were right, his conclusion would have been wrong because, in fact, the radiation to space does not come from the ground. It comes from the high, thin parts of the atmosphere, which are not saturated and which are also so dry that CO2 competes very well with water vapor. So this is, you'll see a pattern building up here. This is one of the examples of a failed prediction in climate science, and you can tote up your scorecard right now. So you can start keeping track. Now, one thing that's common to all the CO2 theories of climate change through the ages from Arrhenius onward through the next 50 or 60 years into this very day is that they all predict that there should be a depletion in the outgoing infrared radiation in the vicinity of the 15 micron CO2 band, or the 660, that's equivalent to 666 centimeter inverses. That's the number of the beast. The universe is trying to tell us something there about 666. But this, and it was, until the space age, you could not actually observe this from space. The red is an observation of the outgoing infrared spectrum. This is wave number here, and this is radiance. The outgoing infrared spectrum as seen by the AIRS satellite, and you can see this dip. That's the visible manifestation of the 15 micron greenhouse effect due to carbon dioxide that was predicted in all of these theories and was eventually observable. And you see the same thing even more clearly on Mars, which is a nicer atmosphere because it has essentially only CO2 in it. There's the 15 micron dip. This is the black body curve. So you see the ocular proof of the greenhouse effect in the sense that Arrhenius conceived it. Now, you'd think here we are at 1900, Arrhenius said one thing, Ångström said something else. There's this mind-boggling idea that humans could change the climate. Everybody in the science community is going to jump on it and really study this to death and decide who is right. But that's not what happened. It fell over like a lead balloon. We had something like 50 years of silence on the specific subject, which I call the dark ages of global warming, of anthropogenic global warming. And I think Paul Hoffman puts this sort of thing in context very well. This scenario for scientific theories he formulated in connection with the snowball Earth hypothesis. But there are these stages, like Elizabeth Kubler-Ross. You formulate and propose a theory, you reject it, then you ignore it, often for a very long time. And that's when a lot of the real scientific progress is made. You rediscover it, and then it's accepted. And we're at the stage now of acceptance, at least in the scientific community, of the standard model of CO2 and climate change. Although that acceptance has not penetrated all of the political sector yet. So what do I mean by the standard model? Particle physicists have their standard model, which makes various predictions, and there is a standard, what I will call a standard model of planetary temperature, which looks a little bit like this. And this will help me put into context what was really going on in various areas of science that helped consolidate the standard model during this long era, dark ages, when global warming was not being directly addressed by the scientific community. And so the situation, if you have a planetary atmosphere, you have a deep layer, which we call the troposphere, which is convective. It's mixed up by convection. And then you have a radiative layer, where the heat transport is by infrared radiation. You have solar radiation, which penetrates nearly to the surface, heats the surface, and stirs up this convection. And the temperature gradient maintained by convection, this reduction in temperature with height, results in an atmosphere which is opaque in infrared down here, being able to emit to space only at these temperatures that are colder than the surface. And that's where the greenhouse effect comes from. If you want to read a lot more than this about this than you ever wanted to know, you can go to the Cambridge University Press stand and buy my book, Principles of Planetary Climate, which Eli Rabbit described as death by theoretical physics, but I think it's a fairly gentle introduction to the subject. But in fact, this is a pretty simple picture. It's even simpler than it looked here, because here we have a top of atmosphere balance, which is purely radiative. We have turbulence and radiation at the surface, but most of this stuff happening at the surface is irrelevant, because all it really does is act to keep the surface temperature close to the overlying air temperature. So you can replace all that surface stuff with just the assumption that the temperature of the ground is pretty close to the temperature of the air. And so it all really comes down to just doing this top of atmosphere radiation balance, which is fairly simple. And that's our standard model. And it's identical to the standard model that was developed in the 1920s for stellar structure. Only turned upside down. In a star, your energy source is down here due to fusion. The convective layer is in the outer part of the star, and you get a temperature gradient with height, which is why the photosphere of the sun is cooler than the interior non-convective core. And the rate at which the star loses energy is determined by the opacity, in this case in the visible light, which determines what the temperature at which the star radiates. The sun radiates at about 6,000 Kelvin, which is a lot lower than the temperature at the center of the sun. So the dark ages of global warming theory were no more really dark than the historical Dark Ages that followed the fall of the Roman Empire. In fact, quite a lot of vigorous intellectual activity was going on during this time. In the 1900s, for example, Frank Very, who was a student of Langley, Frank Very really consolidated the understanding of the temperature of the moon. It was really the first completely consistent calculation of a planetary temperature from first principles. It's a simpler case because it has no atmosphere. And that was confirmed by infrared observations of the moon in 1930 by Pettit and Nicholson. So astronomers were thinking about planetary energy balance all during this time when there was not much attention to the global warming problem. But apropos of the standard model of climate, the equations we use to understand planetary temperature were in fact developed during these dark ages by Schuster and by Karl Schwarzschild, the same as the black hole Schwarzschild, to understand radiative transfer as it applies to stellar structure. And there was one astrophysicist, Robert Emden, who actually recognized that the same equations could be applied to planetary atmospheres, just turned upside down. It was kind of a voice in the wilderness there. Not many people in the meteorological community picked up on that. And then in the 1930s, infrared astronomy was really heating up. There was a great deal of work on observation of the planets Venus and Mars by Gerard Kuiper and others. And a lot of infrared radiative transfer theory was developed in aid of infrared astronomy. This is the same problem as we work on for energy balance. Astronomers were working on it for observational reasons. And somewhere in here, there was even a rather remarkable paper by Hulbert in 1931 in Physical Review, who computed 2 times CO2 warming using something very close to what we would call the standard model, but it picked up it went nowhere. Nobody picked up on it. It shows the lack of attention to the subject at the time. So to get a kind of an idea of just what the meteorological community was really thinking of during all this time, I actually sat down and examined every issue of the Quarterly Journal of the Royal Meteorological Society between 1900 and 1950. I did it online, so it was not too hard. I read all the tables of contents, and I read selected papers in there, and just to get an overview of just what were they thinking of if they weren't thinking about this remarkable hypothesis of Arrhenius. And there's basically not much of interest up until about 1927. But in 1928, there was a kind of landmark event, which was Simpson's memoir on atmospheric radiation, which consolidated Ångström's idea that, Knut Ångström's idea that water vapor was really all that counted, and that CO2 was not especially important. But this was a very fundamental advance in radiative transfer, but it did discount incorrectly the importance of carbon dioxide. And also quite remarkably, there was a quite extensive review of atmospheric radiation by Brunt in 1932, but there's not a word about either carbon dioxide or Arrhenius. How did such an important idea get neglected? Now, the Quarterly Journal was run, and the Royal Meteorological Society was run almost like a kind of a paper blog. People presented these papers in a clubby set in public, and then they discussed them, and then discussions were summarized by the secretary. And this is marvelous. The Lewis Fry Richardson, the founder of numerical weather prediction, said the atmosphere resembles London, for in both there were always far more things going on than one could properly attend to. And I wonder what he would say about AGU meetings, because it really goes in spades with that. But he raises this question, maybe Simpson is forgetting about something, so it's on the radar screen. Was it not possible that some absorption band, which was significant in the kilometers of atmosphere, might have escaped detection in the laboratory? And he mentions Ångström's observations that say something else is an absorber there, and that's not Knut Ångström, that is Anders Ångström, the grandfather of the original Anders Ångström, who is restoring the family honor destroyed by Knut Ångström by restoring this primacy of CO2 and non-water vapor absorbers. And his name will come back in. The Ångströms were like the Trapp family singers of spectroscopy. Now, this dapper fellow is George Callendar, who made a valiant attempt to revive interest in global warming, in CO2-induced global warming. And he mentions that most people seem to think that it's just water vapor that's the greenhouse gas. And he mentions Arrhenius, and I want to point out he mentions Chamberlain, who's one of ours at University of Chicago. I'm very proud to have him listed there. And Callendar did not just compile temperature records. Callendar actually developed a quite good radiative transfer model and applied it to the doubled CO2 problem. And he points to all these new developments in physics that he was aware of that made it possible to do better than what Arrhenius had done, including absorption spectrum of water vapor. And notice also, he is aware of the ocean carbonate chemistry reaction that determines ocean carbon uptake. It's a kind of an urban legend that the reason the global warming idea lay fallow so long was that everybody thought that the ocean would suck up all the CO2. That's not true. The basic chemistry that limits the ocean uptake was already essentially pretty well worked out by this time, although we'll see when it was first, the consequences were first completely brought to fruition. So what happened as a result of Callendar? Did he manage to revive interest? Well, there's a very interesting discussion. The work was quite rightly criticized because Callendar's model assumed that all the energy transfer was purely due to radiation, whereas people were already thinking quite a lot about atmospheric convection at the time, and also the large-scale circulation of the atmosphere. And so it was criticized because it neglected all these other heat transfer mechanisms. But in fact, astrophysicists, working independently of meteorologists, already had largely resolved this issue by radiative-convective models, which were completely standard practice in astrophysics, but there was no technology transfer, no knowledge transfer between what Callendar was trying to do and what the astrophysicists were trying to do. But a bigger problem not picked up in the discussions was that Callendar was trying to understand the temperature increase in terms of the surface energy budget, which is of secondary importance to the top of atmosphere energy budget. And he forgot the lesson that Arrhenius already established, that is the top of atmosphere energy budget, that is the key to warming. It was ignored, and though Callendar actually continued publishing all the way up to 1961 when he saw the beginnings of the revival of the CO2 theory, the work really did not take off, and it's rather peculiar. Oh, there were various other things that happened, but there are a lot of developments in radiative transfer theory. Goody came on the scene in 1951, but the first paper to actually reintroduce CO2 and discuss and revive Arrhenius, the first citation of Arrhenius in Quarterly Journal since the paper by Callendar, is by Plass in 1956. I'm not sure exactly what made him start to think about this. There were a lot of observations of the stratosphere coming in. So he actually looked at the 15 micron CO2 band and he estimated the warming due to 2 times CO2. But his prediction was still incorrect. It was a still incorrect implementation of the standard model because he too, like Callendar, was trying to do everything in terms of the surface energy budget, keeping the atmospheric temperature fixed, which is inconsistent. So, actually, how do I go backwards here? I use the what? Oh. Yeah, I don't want to miss this one. So, the other thing, this is where I came on the scene. And I'm the one on the left. This is my friend, Eli Rabbit. I don't know if he's here. It's okay. It's a cute picture, but I'm showing this partly because it feels like such a privilege to have lived through this historical era when so many new ideas about climate change came in, and to have actually been able to know personally essentially everybody that I'm going to mention in the rest of this talk. And it's a breathtaking degree of progress in a rather short amount of time. So in the 1960s saw a lot of activity both in earth science and planetary science in thinking about planetary temperature. And we come to another one of our successful predictions. This is done by Carl Sagan, who correctly inferred that the microwave emission of Venus could only be accounted for by a hot surface maintained by the greenhouse effect of a very thick atmosphere. And using the standard model in pretty much the form I outlined it. He predicted that Venus has a 50 bar surface pressure. That was a prediction that was tested when the first descenders made it to the surface of Venus in between 1967 and 1970, and it was not. And he was off. The actual number was 90 bars instead of 50 bars. But compared to how piddling little amount of CO2 we have in our atmosphere, I think that's a pretty good prediction. But Sagan was coming up through the astronomical end of things that tracks back to Schwarzschild. He cites almost essentially nothing in the meteorological literature in support of his development. This developed along a completely parallel track. Now, in the 1959, there was another remarkably successful prediction. Remember those carbonate chemistry equations I mentioned? Bert Bolin was the first to really formulate a mathematical model that that takes carbon dioxide emissions and models ocean uptake of carbon dioxide correctly, incorporating both the mixing between the surface ocean and the deep ocean, and also including the carbonate chemistry that turns dissolved carbon dioxide into bicarbonate. And he turned that into a prediction. His prediction, this is the year out to the year 2000. In 1959, he predicted this envelope of atmospheric carbon dioxide concentrations based on economic projections of how much CO2 we would emit. There was no data on the trend at the time. Certainly there was no data in 1959 on what was happening in 2000. But there wasn't even any historical data at the time. That came in through ice bubbles. But you can see here's what the atmosphere actually did. And as in so many things, the scientists were kind of conservative about what was happening. Things tend to be coming in at the high end of the predictions of the scientific community. But this is a remarkable prediction. It shows we really do understand the chemistry and physics of ocean carbon uptake. Okay, this is what I was doing in 1967, and this is what Manabe was doing in 1967. Darn sight more important. This paper in 1967, which was a radiative-convective model of the warming due to doubling of carbon dioxide, was the first completely correct radiative-convective implementation of the Standard Model. It was the first time that Arrhenius' principle of top-of-atmosphere energy balance was brought together with correct spectroscopy and a correct role for convection. And so this, I think, is the first quantitatively respectable prediction of the amount of warming you get from doubling CO2. Now, in this model, like all radiative-convective models, he put in water vapor feedback by fiat by assuming a constant relative humidity. That's pretty much all you can do in a radiative-convective model. And he gets a 2 degrees Celsius warming for doubling of carbon dioxide. So this is the first quantitative prediction. And it also predicts that tropospheric warming would be accompanied by stratospheric cooling. I've colorized his graph so you can see it better. So these there are 3 lines here. This is temperature versus height. This is high CO2. This is a low CO2 case. And the high CO2 case is warm near the ground, and they cool up in the stratosphere because carbon dioxide increases the efficiency of infrared cooling in the stratosphere and helps to get rid of the heat that is deposited by absorption of ultraviolet due to ozone. And this is the verification. This is Gillette, 2011. The stratosphere is indeed cooling. We know a little bit more about this than Manabe did. There's a role for changes in ozone and so forth, but that was correctly predicted. And of course, not only is the stratosphere cooling, the troposphere is warming. This is a compendium of satellite and radio sonde data. Stratospheric cooling, tropospheric warming. This is these are tropical trends. And I'll come back to the vertical structure. Now, you have to wait until 1975 for the first really major, next really major advance. And this is when Manabe and Weatherald did the first general circulation model simulation of the world with doubled CO2. So they coupled the radiation into a full fluid dynamic model. And this was very important because relative humidity and the water vapor feedback is the reason that the warming is enough to be a source of concern. In the radiative-convective model, water vapor feedback was essentially put in by fiat. You assumed the relative humidity stayed constant. But you don't assume that in a general circulation model. The atmospheric humidity is computed dynamically, and so the water vapor feedback is an a priori emergent property in such models. In addition, you no longer have to assume that the model has a fixed convective vertical structure in the troposphere. You actually compute that using a combination of convective influences, radiative influences, and fluid dynamical influences. And he also put in ice and snow albedo feedback. And this is their prediction, again colorized. This is the warming, this is the latitude height structure of the warming. That's the equator, that's the pole. And there's your stratospheric cooling again. And here you see that the warming in the polar, and you see the polar amplification. You see polar amplification. Now that's not necessarily a signature of CO2 alone. Almost any kind of warming will do that. But the verification of this is an important test of how well our models are able to capture the collective behavior of the atmosphere. So you have this bottom trapped warming in the polar regions, and then you also see something that we didn't see before, which is that in the tropics you have vertical amplification of the warming in the troposphere. And that is because in this paper Manabe used the moist adiabat as the basis for the convection scheme rather than a fixed lapse rate. And so that gives you vertical amplification. Now, this predicted the polar structure, the bottom trap polar warming has been verified by data. There's a paper by Cerise. The polar amplification is so strong you don't see any contours of the warming over here. I'll show you a separate figure with that. But the vertical structure, both the polar amplification and the vertical structure, which is an emergent property from the general circulation model, is verified by the actual data. Now, something that is still waiting to be verified, where the data has not given us a strong enough signal to do the verification yet, is the issue that predicted by Manabe, the fact predicted by Manabe, or the behavior that the tropical warming should increase with altitude. The gray area is what general circulation models predict for the vertical structure of warming. This is an attempt to reconstruct that using the thermal wind balance that Steve Sherwood did, but there are lots of, but while we can certainly say incontrovertibly that the tropical troposphere is warming, the error bars in the data are really not good enough yet to say we've detected the signature of the vertical amplification yet. We haven't falsified it yet either. Now, here's another significant thing. I'm going to concentrate on Suki's papers because often he was there first, but at this time there were two other models, that the NCAR model and the GIST model, that were making important contributions. But in the interest of time, I'm just going to concentrate on Suki Manabe's thing. So this was the first coupled ocean-atmosphere model, it was the first prediction of the transient warming. So this is something that you can really begin to compare with the detailed patterns of warming in the data. So this was a doubled CO2 calculation with gradually increasing CO2 and a fully dynamic ocean. You see the polar amplification, or the Arctic amplification, just as before. But you see something new, which is that now we see that the land warming is amplified relative to the warming over the ocean. And that's very important because people live on land. So the fact that you have amplification on land over ocean has enormous consequences for the impacts of climate change. You also see that the warming is attenuated in the whole southern ocean, and they have a description, they have a discussion of why that happens. They get this rather curious cooling over parts of Antarctica, and you'll see when we talk about verification that there are still problems with what models are doing over Antarctica, but overall, this is the actual temp warming pattern to date. The model failed to predict the strong warming over the Antarctic Peninsula, but it did get this land amplification, and it did get the attenuation of warming in the Southern Ocean due to heat uptake by the Southern Ocean correct. So that's another successful prediction, one which involves quite a lot of detailed model physics. Now, to take an example from paleoclimate, in 1981, the Climate Project reconstructed temperature of the world's oceans during the last glacial maximum, and you expect everything to cool down because the CO2 was lower, you had these big ice sheets, but strangely, they did not find very much warming, found only very weak they did not find very much cooling in the tropics, in the tropical oceans. And that was a big problem. We all started to think, I remember this, we all started to think, oh, my God, there must be something wrong with all the models. Because all the models, there's something missing we don't understand about climate physics. All the models predict, this is latitude versus, this is temperature versus latitude, again, colorized, Broccoli and Manabe, 1987. All the models give you quite substantial cooling right through the tropics. So what was wrong? Now, also Rind and Petit found indications that models, when forced by CliMap SST, produce a snowline depression that is incompatible with the observations of tropical snowlines. So something seemed to be wrong with the models. Dick Lindzen came charging to the rescue with a paper that fed off of one of his early papers, and he explained why the lapse rate should change in a way different from the moist adiabat, and all the models were wrong. And he explained CliMap very nicely. And a corollary, we'll see a pattern building up here, a corollary of this theory is that the climate is very insensitive to carbon dioxide. So, there we go. So he had a nice theory that explained nice data, and but then CliMap started to unravel. The thing he explained disappeared. First indications that the CliMap was wrong were from strontium-calcium ratios in coral by Fairbanks, and soon many other proxies came in. And this is a current reconstruction by the Margot team using multi-proxies, which there's still some regions where the tropics doesn't cool that much, but the tropics cools a great deal more than it does in CliMap. So basically, it was a case where the models were right and Lindzen was wrong. So it's okay to be wrong, and Dick is a smart person, but what people don't really understand is that one way of using your intelligence is to spin ever more clever ways of deceiving yourself, ever more clever ways of being wrong. And that's okay, because if you're wrong in an interesting way, that advances the science. I think it's great to be wrong. And he's made a whole career out of being wrong in interesting ways in climate science. I won't go into the details, but there were things that were wrong, that were inconsistent about the generation of buoyancy in the convection model. There were even some errors with negative emissivities in the radiation code, which are not the interesting parts of it, but it was the water vapor parts of it that were wrong in a more interesting way. And speaking of cases where models were right and the so-called observations were wrong, there's the famous case of Christie and Spencer and the microwave sounding unit satellite data, which seemed to be saying that contrary to everything I was saying about the atmosphere and surface warming together, and everything the standard model predicts, the surface might be warming, but the atmosphere doesn't seem to be warming. The atmosphere is actually cooling, so there's something really wrong. It's not CO2. But this turned out to be wrong. Once the errors in their satellite retrievals were corrected, then there was complete compatibility between the surface warming and the warming of the troposphere. The troposphere was indeed warming along. Another case of wrong is of a wrong prediction was remember I said water vapor feedback is essential to CO2 being a significant threat. It's the amplification from water vapor feedback that makes doubling CO2 a big problem. And Lindzen then went after water vapor feedback directly in 1990 with a theory that predicted that actually water vapor feedback would be negative. The atmosphere would get drier as it got warmer. And this is a figure from the paper you might recognize if you went to the Bjerknes lecture by Bob Howes, that this is a picture of convection that was already obsolete in the 1970s, and that was one way that the theory fell apart. But there are many tests of the extent to which the atmosphere actually does get moister as it gets warmer. We can't very easily detect the trend in water vapor yet, but there are a lot of natural experiments like ENSO and volcanic eruptions and so forth that essentially confirm that the way the models do water vapor is right, and the atmosphere really does, on the whole, get moister as you get warmer. But those theories are at least falsifiable. As I say, it's great to be wrong. And actually, I entered the water vapor field partly as a result of being annoyed that what Dick was saying about this and wanting to prove him wrong. I knew it was wrong, and I but you have to turn that into an argument. And that's how science proceeds, through people proposing things that get other people kind of wound up, and then we all do better. But then there are other things that are not so great. There are theories that are not even wrong, in Feynman's term, things that are so badly formulated that they don't even make a prediction that's falsifiable. And this one by Cortiot, for example, on supposed connections between the Earth's magnetic field and climate. It can't even keep straight what the sign of the effect is from one end of the paper to the other. They literally switch the sign of what they think the effect is from one side to the other. Now this is a paper. Now a lot of you have just been in the Schneider lecture. This is a paper that was wrong. A paper by Rasul and Schneider that was wrong, but it tells us a lot of things. This paper by Rasul and Schneider, 1971, made the claim that the cooling due to aerosols would outweigh the warming due to CO2. And it was wrong because the model of aerosols used was primitive and exaggerated the albedo of the aerosols, but it was wrong even more because there were some errors in the radiation model which somehow were not caught by the reviewers, probably because not too many people were thinking about global warming at the time. And so they vastly underestimated the CO2 effect. But science is self-correcting. The problems were found, and this was dismissed by 1975. And in the mark of a good scientist, all good scientists are skeptics, and a good scientist changes his or her views when new data comes in, and is not wedded to finding one theory after another that gets the same result as before. And that is a hallmark of Steve's career. He certainly is a great scientist. So we come to the end now. And back to why do I say Arrhenius predicted things correctly? And also make the point that when I say we have a lot of successful predictions and no actually outright wrong predictions, I don't mean to imply that we predicted in advance everything of importance about climate change. And this slide illustrates what I think is the most important thing that we failed to predict in advance. And let me just walk you through it. This red line is what you get. The black line in both of these is a smooth version of the observed surface temperature record. Okay, and so it has a period of rapid rise, a flat period in the 1950 to 70, and a period of rapid rise. It's the same black line in both of these. Now, what you would expect if you take the radiative forcing of all greenhouse gases and then turn that into a temperature, taking into account the delaying effect of the ocean heat uptake, you get this red line, which is the sort of slow rise and a more rapid rise as the greenhouse radiative forcing starts to take off more. So you get a monotonic rise with a kink here, but you don't get this flat period where warming was interrupted in 50 to 70. So of course there's been a lot of fundamental work on this now, but it's all in the nature of things where you're trying to understand what happened after the fact. It's ex post facto, not predicted in advance, and we still have not come to a completely satisfactory understanding of what's going on here. There are two different possibilities that are kicking around, and the truth is between these two extreme limits. One possibility is that the ocean heat uptake has decadal fluctuations, and we know that's true to some extent. There's the AMO, the multi-decadal oscillation, which K.K. Tung has done a lot to diagnose, and it's really there. Models do not do the multi-decadal ocean heat uptake fluctuations well at all, which is why these things were not predicted in advance. And so one possibility is that if you take a low climate sensitivity, and by low, it's not at the low end of the IPCC, but it's similar to the climate sensitivity in Manabe and Weatherall's paper. You take a climate sensitivity that's kind of on the low end, then you could say that what we're seeing is a decadal ocean fluctuation around this upward trend. And so that is a world that has significant but somewhat lower climate sensitivity than the IPCC mean. The other possibility, which was put forth most cogently in the IPCC second assessment report, is that it's not the ocean, it's aerosols, because we've been putting out aerosols, and back here you have volcanic eruptions, the cooling things down. Because greenhouse gases are not the only climate forcing, because we've been putting out aerosols as well. The aerosols have taken away from some of the warming that would have been caused by greenhouse gases. And so in that case, you get a situation like this where we can fit the data by saying we have a high climate sensitivity, 3 Celsius per doubling, and this actual trajectory takes into account the ocean heat uptake. You have high climate sensitivity, 3 Celsius per doubling, but the real world is coming in below the greenhouse prediction because there's an aerosol cooling effect. Now, this is a somewhat more benign world than this world, so it's very important to know which one of these is the truth because of our lack of knowledge of how aerosols affect albedo, especially how aerosols affect the albedo of clouds. We don't actually know where truth stands between these two things. But this is a much more dire scenario, and I especially recommend a paper by Armour and Rowe in GRL about the consequences of whether you're in this kind of world or this kind of world. In this kind of world, this is a much more dire world, a much more bleak world, because not only is the climate sensitivity higher, but because aerosols wash out of the atmosphere in only about 7 days, when you do finally see the light and stop burning coal, you lose your aerosols, you lose your sulfate aerosols, and so not only are you contending with all the warming all the warming due to CO2, but all the radiative forcing due to CO2, but you get the extra boost from all this unleashed or unmasked radiative forcing that the aerosols were doing. And the warming you get in response to that is responding to a high climate sensitivity rather than a low climate sensitivity. It's almost certain that there is a substantial aerosol effect, but it's also, this pendulum is swinging towards thinking that maybe there's more ocean decadal variability than we thought in the past. But this is something that it would have been nice to have predicted in advance, but we did not. So now, I think that the standard model has done pretty well. I think our predictions have been verified pretty well. There's been a constant challenge and testing over the last 100 years of the connection, the theory of the connection between carbon dioxide and climate. So I think we in climate science have earned a right to be listened to. And the question, though, is anybody actually listening? If you make a prediction in the forest and nobody is there listening, have you actually made a prediction? Has it done any good? And will this be the epitaph for human civilization? Will dedicated, impoverished geologists of the future scrabbling through ancient texts and ancient AGU abstracts, trying to figure out what the heck went wrong and why isn't there an AGU fall meeting anymore? Will they be looking and say, well, we were given fair warning, but we did it ourselves? That would be the hard landing when we just continue utilizing all of our fossil fuel resources until we run out, and then we have a world where possibly agriculture has crashed. We've changed the climate for the next 20,000 or 100,000 years, and created a world that our ancestors our descendants will have to live with for probably much of the rest of the lifetime of the human species, despite the fact that we were warned that we should do something before we bring on this hard landing. There's another storyline. I like science fiction, and this book by John Brunner, Crucible of Time, is about these creatures who 1,000 years in advance, through their primitive astronomy, recognize that there's an existential catastrophe awaiting them out, and that they need to mobilize their society to do something about it over the next 1,000 years. And they do. They do. It's a struggle, but they do. But humans have met many challenges before, and I don't know why we should feel so timid in the face of this challenge we have right now. But we don't have 1,000 years to do something about it. We don't even really have 100 years to do something about it, because the amount of carbon we pump out in the next 50 years or 100 years is going to determine what climate humanity will have to live with for essentially most of the rest of the lifetime of our species. So I do have hope. It's encouraging that President Obama mentioned in his acceptance speech that we want our children to live in an America that isn't threatened by the destructive power of a warming planet. But now I hope that these words will not just be words said one night and forgotten and thrown away. I hope the leader of the free world will lead the world into the future where we can write the happy ending. Thank you.
Thank you, Ray, for a superb lecture. I'd like to just mention that Ray and David Archer published a book, I think it was last year, an edited book called the Warming Papers, which brings together a collection of many of the historical articles that he mentioned with a very, very astute and insightful commentary on each of those papers. So if you want a really nice synopsis of the whole history of global warming science, that's the book to get. I think it's Cambridge University Press.
That one's Wiley.
Wiley, okay. And also, I think I'm right in saying, Chuck, am I right in saying this lecture is recorded? Yes. And it's available online, so if those of you who want to use this excellent overview for teaching purposes, I'm sure you can get it from the AGU website.
There's a link to this one as well as the next one, the previous one, on the AGU Global Environmental Change website homepage,
gec.agu.org, and you can find
all be available online
next week. Thank you very much. And are there any questions? We have a few minutes. Yes, Lawrence.
Oh, actually, I wasn't. That's interesting. I wasn't aware of Manabe and Delworth. One of the issues that K.K. Tung has noticed is that although some models do have multi-decadal oscillations, first of all, they have different periods. They tend to have periods that are shorter compared to reality. And so, although maybe it would be hard to know which model had the right period. And so based on the ensemble of models that are out there, it would have been hard to predict this. But then there's an important scientific question. What is the predictability of these multi-decadal oscillations, given our lack of knowledge of the initial state of the ocean? It could be like ocean weather, that no matter how good our models were, we wouldn't have been able to predict it because we don't have the right initialization.
Any other questions?
Yes? Yeah. No, yes. So the question is, actually, let me roll back. Right. So the question is, so you still have this this ramp pack, this interruption in warming, and so here in this extreme view, it's not multi-decadal ocean observations that are causing this pattern of rapid rise and flatness. The assumption here, which is actually the standard second assessment report assumption, is that you had a rapid rise in sulfate emissions here, which outstripped CO2 and caused it to be flat, and then eventually the CO2 rise caught up with it. And in the aerosol scenario, it becomes a little bit harder to say what's going on back here. One of the things that is happening back here are there's some volcanic eruptions, but then it becomes kind of accidental that you had this. But the world is only one realization, and there are random perturbations going on there. But that is the standard. What you have to believe if you want to attribute this to aerosols is that you had a rapid rise in the aerosol contribution here and something else going on back here. But of course it could be it's probably a combination of both the ocean and the aerosols. Oh yeah, yes, back there. Right. So the IPCC predictions are the IPCC predictions for warming incorporate the rise in aerosol loading, and so they're part of the curves. My curve here is a kind of a schematic curve, but the sort of thing that would give you this pattern of relatively fixed aerosol cooling over this period would be an assumption, which is partly verifiable, that the increase in Chinese sulfate emissions has been offset by the Clean Air Act sort of stuff in the developed world, so that the aerosol, the net aerosol cooling hasn't increased that much since this period there. But one of the problems is that converting sulfate emissions to albedo is still a rather difficult thing, especially given the difficult question of how the sulfate aerosols affect clouds. And that's why you can actually spin several different stories with different climate sensitivities, all of which can be made to fit the data that we have. It helps in constraining climate sensitivity to be able to look back into the last glacial maximum and other times in the past as a cross-check that doesn't have these same ambiguities. Yeah, yes, over there. Well, unfortunately, I see lots that are feasible, but they all terrify me. Well, except let me clarify a bit. Some people refer to schemes for taking CO2 out of the atmosphere or sequestering CO2 as a form of geoengineering. Those I find relatively benign because they put the climate system back in the state that it was in before we started messing with it. The feasible geoengineering things, technologically feasible, that scare me terribly are the crazy ideas to make artificial volcanoes and put sulfate aerosols into the stratosphere. And the reason I think those are barking mad is that you have CO2 will continue influencing the climate out for 10,000 years. You have to renew the aerosol forcing every 2 years or so. And so you are assuming that somehow society will stay together for the next 10,000 years and be able to jam up these extra aerosols every 2 years or so out onto longer than there have been human civilizations practically. And if you ever stop, then the aerosols go away in a couple of years, and then you are hit with the full force of global warming in a time scale that is determined just by the ocean relaxation time. Unfortunately, I think these sulfate aerosol injections are probably economically feasible. You don't have to inject too much up there. But it puts the world in a state that I call Damocles' world. It's like the sword of Damocles, which is the radiative forcing of CO2 just waiting to clobber you anytime someone stops putting up these aerosols. In addition, we don't actually know enough about aerosol formation and about response of models to aerosols to begin doing this kind of fine-tuning, to even figure out how much we should put up there. There's some very good work by Leslie Gray at Oxford that shows how actually the modeling technology is not even up to doing this adequately, despite what some aggressive proponents of geoengineering say. Okay, yes, it sounds like the time to wind down.
I'm sorry, we have to close there. Well, thanks a lot.
Thank you.